26 out of 250 300. Go ahead, JetBlue 215.
So I'm here on 134 750, which is Boston Approach West. And how do I know what frequency I'm on? Well, I have a dial. Oh, well, how do I find out how to mark the dial? I used my scanner over here. Let's turn that on. And basically, let's turn down the volume of the super regenerative, bring up the volume of the scanner. And now all we do is we go up in frequency until we hear the rushing sound of the super regen. There we go. Okay.
17,500 feet. I was wondering if we would climb up to 12,000 and they would
34 750.
we'll be up there for about 20.
And then turn the super regen back on. So we've determined that we're on 134 750.
3532
So as you can see, the scanner and the super regen are about equal in sensitivity. Both are limited by noise, of course.
4532, up to 60. 3532, good day.
So this is the unit with the 6AW8 inline, which is the audio amplifier, the triode section, and the pentode section both in line. We don't need to use our little speaker amplifier, our little anemic speaker amplifier anymore. We now have a real amplifier. And got plenty of volume. I'm pretty happy with this setup. And I'll publish this basic schematic. So this is the basic receiver. Everything is working as advertised. This is the important stuff. So what are we looking at here? This is the most important part of any receiver. It doesn't matter if it's a software-defined receiver, an old-fashioned analog scanner, or in our case, the super regenerator. If you can get the antenna outside, you stand the best chance of hearing aircraft signals. Let's look at some of the characteristics of this simple dipole antenna, which is a foundational antenna when we're talking about picking up aircraft. First of all, you notice the antenna is in the vertical plane. That's because aircraft generally use vertical polarization, as do the towers. Also, notice it's a pole-mounted antenna, and it's spaced so that the pole actually acts as a reflector. So now we can swing this antenna in any direction and we get a nice big lobe in the direction that it's pointed. Is this gain? Yes, this is the definition of gain. You can get probably 4 to 6 dB of gain just by mounting the antenna at a critical spacing to the pole. The dipole itself, each element is about 22 inches or about 500 to 600 millimeters long. And you can see there's a wrap of coax. Let's go in there and look at taking this piece of PVC and painted it black. I've run the coax up the line and drilled a couple of holes and made a choke balun out of the coax just before the dipole feed. This helps to remove common mode noise that might come down the line, and it makes a balanced feed point for the dipole. You can use RG6 for a 75 ohm system or some type of 50 ohm coax such as RG58 or LMR 240. So this is the basis for a good aircraft antenna. Let's look at a quickie version of this. In this case, I've just taken a BNC connector and put a couple of pieces of stiff wire off it. No choke, no nothing. Even this is producing good results. And in this one, we're going to take a look at a Heath Kit classic, the Heath Kit Tour. The Tour was a transceiver that Heath Kit put out in the early 60s. And this super regenerative circuit is a little bit different. So I'm going to go through that. It is based on small dual triodes that were used in the late 50s and early 60s for the front ends of television sets. So this is a tube that has high gain, low noise, and is well suited for broadband operation. We're going to build out the circuit, get the audio section working. Also, I'll be able to do a little more fooling around with the circuit to try to optimize it for wideband tuning. So this super regenerative receiver is going to be a little bit higher performance. It's going to have an RF amplifier stage, the super regenerative stage itself, and then it's got some audio amplification that we're going to be adding, hopefully enough that we can drive a speaker. Typically, I don't like to put the AC power supply in the same box as the small receiver. I prefer to use an external power supply. That allows the power supply to be used on several projects, and it's not dedicated to the receiver. Transformers, chokes, and power supply components get expensive, and I don't like buying those parts for every single project. So I prefer to put the power supply in a separate box and then just make different types of receivers, transmitters, amplifiers, and other electronics that can be powered off the supply. So the metal work is not complete. I haven't gone as far as to mount the terminal strips, but I have the tube sockets mounted. I have the output transformer, and you can see I've got some controls on the front. I'm not even sure exactly what the two on the right are going to be, perhaps the volume control and the regeneration control, but I haven't assigned them yet or picked parts values. We have the variable capacitor that's going to have a large knob on it. On the rear, I've got a terminal strip that's going to be the power supply input. I have a phone jack, and I have the antenna connector. This antenna connector happens to be a 75 ohm BNC that I had left over from something. I think I'm going to use 75 ohm cable to the antenna, so by accident that works out pretty well. So this just shows the inside where we have the parts mounted. Lots of ground lugs all over the place because you want to keep your ground short at VHF. If I had to do this over again, I probably would have put the tuning capacitor a little closer to the tube. At this frequency, it isn't going to make much difference, but that's quite a gap between the super regenerative receiver and the variable capacitor. A little more than you would like for a VHF circuit. So that's the basics of the start. Now, what type of super regenerator are we going to use? I've decided that I'm going to reproduce pretty closely the super regenerative receiver in the famous Benton Harbor lunchbox known as the Heath Tour. Now the Tour was an entry-level AM transceiver kit that came out in the mid-60s, and at that time novice operators could use 2 meters on phone. That's the only time that novices have had phone privileges, at least in those days. That did go away, and novices were kicked off 2 meters, and you had to get your technician license in order to use VHF. So if you look at the schematic of the tour that's in the back of the manual, this section over on this side is the Super Regenerative Receiver, and down here is the audio stages, which in the tour actually do double duty as modulator and as the audio output for the receiver. So that's the basic circuit. This is a different type of Super Regen receiver than we've built, so it should be interesting to go through the circuit and see how this performs compared to the two that we've built so far. One thing you'll notice is that in the tour they used a standard V3A, the 6BS8, the RF amplifier, the low noise RF amplifier, is a standard type amplifier. It's not a grounded grid amplifier. And if you're doing a narrowband circuit, just covering a few megahertz, this type of circuit makes a lot of sense. However, we want to cover the entire aircraft band and maybe a little more. So I'm going to be using a grounded grid type amplifier for our circuit. So we do have one difficult choke to build, and that is, or procure, that is this 75 millihenry RF choke that's associated with the quench frequency. They're trying to develop something like a 20 kilohertz quench frequency, which is quite low. I initially tried to build it on an ordinary iron core slug and ended up with a bunch of number 32 wire on there, and I kind of gave up. I ended up with a nice 4 to about 7 millihenry adjustable coil, so not 10 times lower than what we really need, so that wasn't going to work. But then I remembered in the old days they used to have these 88 millihenry telephone chokes that were surplus. People have these all over their junk boxes and don't know what to do with them. So presumably half of it would be 44 millihenries, and together it would be 88 millihenries, and that's kind of in the ballpark. I've got it series 8ing now, and I'm reading about 87.5 millihenries, so it's working. So if I wanted to really get technical, I could start removing turns until I get it exactly down to what they want. But I'm going to use this thing. It's going to look silly in there, but we're going to finally find a use for one of those old 88 millihenry telephone transformers. So I removed 18 feet of wire from one side of the 88 millihenry coil. The two sides are series 8ing, and we now have our requisite 75 millihenries. It's resonating at 21 kilohertz with a 0.001 or 1000 picofarad capacitor. There's an entire science devoted to mounting of toroid coils to chassis, some elaborate FR4 washers and nylon hardware and all kinds of interesting things. But my lazy man's idea is simply to use one of those mounting bases and run a tie wrap through it and just zip through the toroid. Okay, next we have to come up with the plate inductor of the RF amplifier stage. Now this is going to be a slug-tuned coil. It's going to be a broadband slug-tuned coil. And now you guys are saying, oh my god, I have nothing like this. If we run into trouble, we might be able to replace it with an air-wound coil and a trimmer. But I would rather use something like these coils in that plate circuit. And so look in your junk box. Maybe you have one of those old Toco coil kits or some slug-tuned coils. They have to be basically, you'll be able to tell they're VHF coils because they will not have very many turns on them, if they have turns on them at all. So these are all good candidates for that plate coil that goes into the grounded grid amplifier. The cathode feed into the Super Regenerative Receiver to bring the cathode above ground enough to couple the signal in. I thought I would try to wind one though on a simple wooden dowel. I've got two pieces of number 28 wire. They're different colors just to make it easier to see what's going on, but you can just double over the same wire and use it that way. And if you get confused, just buzz out the leads. I'm going to wind as many turns as I can on this. Okay, the next step was to twist up the wire. I did this with a hand drill. It's approximately 5 twists per inch. Or you can go online and order a pair of 1.8 microhenry chokes. Probably 1.8 or 2.2 microhenry standard chokes will work fine. I've got a pair of homemade 1.8 microhenry chokes. There's simply some wire wrapped around this pen, 25 turns. Now, when you've got the thing working right, it will go into regeneration fairly smoothly. You want to run it just beyond the point it starts. That's where it's the most sensitive. If you keep going, it may handle stronger signals better.
If you guys got something you might think of. 6,000, direct Manchester. 2.75, Bravo. 4532, up to 60. 3532, good day.
So this is the unit with the 6AW8 in line, which is the audio amplifier, the triode section, and the pentode section both in line. And got plenty of volume. I'm pretty happy with this setup, and I'll publish this basic schematic. Something I noticed right off the bat with this is that I undersized the potentiometer, and it should be an audio taper. Also, it's very bright sounding, so I need to increase the value of the cathode resistor on the power amp and bump up the coupling capacitors a little bit. We've lost some of the low end on the audio. So I've done some audio mods, and I wanted to show you what a proper log pot can do. See how that works? That's a more natural volume control. Just like you want the regen to go in slow. Something that I haven't talked about now that we have the receiver basically working. What kind of a speaker can you drive with a simple amplifier like this? And you've heard people say, oh, you need to use a small speaker because you don't have a lot of power. Well, if you have a large speaker like this one over here, and it happens to be something that's designed for 5 or 10 watts, it's going to be very efficient. And it probably is going to sound a lot better than a small speaker like this. So let me turn this up to the paging band so we've got something to listen to. Okay. Some paging. Okay. Now I'm going to plug it into the bigger speaker. Let me get this in here. So definitely getting more lows out of the speaker, but there's really no real sound difference. The large speaker is being driven quite nicely. Okay, I wanted to let you hear this whistle. I don't know if you can hear it. You hear that? That's an effect I wanted you to hear. That is a harmonic of the quench frequency in the VHF band. So when you hear something like that and it varies with the potentiometer, that's an actual harmonic of the quench frequency, another shortcoming of the Super Regen Receiver. Now remember, I have been trying to follow the Heath Kit circuit as close as I can, including the two chokes on the filament and the cathode raised above ground. But curiosity got to me, and I wanted to find out what would happen if I just ignored the filament, grounded one side of the filament, and sent the 6.3 volts to the other side and just put a capacitor across it, and then treated the cathode as a separate entity and just put in a simple choke from the cathode to ground. And you know what? I think it worked better. The only symptom that seemed to ring true was that the frequency shifted down. So definitely more capacitance doing it this way. By lifting the filament and the cathode off ground, there is no doubt that it reduced the capacitance on the tube, and it will allow the tube to work at much higher frequencies. That's why they do it. But because we're at a rather low frequency down in the aircraft band and not up at 400 megahertz or something, or some other higher frequency, there's no need to take the best practices approach of using two chokes. So I got away with just one of those homemade chokes and took out that fancy bifilar wound and threw it away. So all I really needed was just a simple hand wound choke, and it worked just as well, if not a little better. So a mystery control has showed up. A potentiometer, which I've added to the circuit. Basically, if I can get the camera around here, you can take a look. I've added a potentiometer inside. This potentiometer is an idea that I've been seeing all over the internet. Basically, it's a biasing pot that goes on the bottom of that same choke we've been talking about. And this puts a few volts on the cathode of the tube and stabilizes it. Remember, the desirable characteristics we're looking for are being able to go into regeneration smoothly, being able to tune across the whole range without any blocking or suckouts. Picking up some nice paging signals. It'd be interesting to put a decoder on this. I'm sure it would decode the paging just fine. Critical here. As you can see, the biasing does adjust how the regeneration goes in. What I was hoping with this control was to be able to improve the audio distortion situation. The Super Regen's not the greatest as far as fidelity and audio distortion goes. I didn't see a big difference fooling around with that bias pot, but the jury is still out. We'll see if this is worth putting in there, or if it's just another one of those things that people do because you see it in the literature and in the schematics and you just do it. Okay guys, this is my first time using a screen capture device, and it's time to go through the circuit diagram of this Super Regen that we ended up with. Of course, we know it's based on the Heath Kit tour schematic with some modifications and innovations along the way, like that choke rework that we did here. First, let's review what is the mechanism that allows self-quenching in a one-valve circuit. You may remember that quenching is the action of taking a regenerative receiver that's equipped with excess feedback quickly in and out of oscillation. This can be done with grid bias or power supply amplitude modulation. Usually it's a little of both. The key to understanding self-quenching is to think about the factors that cause motor boating and how we prevent it in amplifiers and radios. Typically the problem occurs when the high voltage DC supply, usually the high voltage source for that stage, is not a low enough impedance, so the supply can become perturbed or pulled around in enough of a swing that a never-ending oscillation sets up. We call this squegging in the ultrasonic Super Regenerator, and we call it motor boating in low-frequency audio amplifiers. How do we fix motor boating? We generally replace the leaky or high-impedance bypass or electrolytic capacitors, and it becomes all good. Regulation from a low-impedance source is the key to eliminating motor boating. So we want just the opposite of this. We want to deliberately underfilter or bypass too lightly at the quench frequency. Add some high impedance in the form of a big resistor or choke in the power line, and this is bound to cause some trouble. We control the values to make this occur where we want it, from 20 to usually 100 kilohertz. Most people like to use a lower quench frequency. So we have a 0.001 plate cap right here. This is great for bypassing RF. It's not so great for bypassing the quench frequency. So how about this big 75 millihenry choke? That's going to put some impedance in series with the line. And of course, this is all setting you up for the quench frequency motor boating. That's for sure. So let's start with going through the whole circuit. Start with the front end over here. V1 is the grounded grid RF amplifier. As you can see, we have L1, which has a high impedance, or a high enough impedance, so that our 75 or 50 ohm antenna input is not attenuated, but lower frequencies are attenuated. R1 and C2 make a slight bias for the stage to put it into class A. We don't need to have it exactly in the middle of the load line because we're talking about microvolt level signals here. We just need to get it conducting enough to amplify through the stage. I've added a type 43 bead. This is just to eliminate the possibility of microwave frequency parasitics and so on. L2 is a broadband coil. Basically, we do not want high Q here. We want to be able to have amplification and isolation over the whole range. And the range, in this case, with the 15 picofarad tuning cap, is around 120 megahertz to 155 megahertz. This is where we want the high Q. We want it here. So by taking the signal and injecting it in the cathode of the tube rather than the grid, we don't spoil the Q, and it tends to isolate us somewhat from the tune circuit, and that reduces the chances of the suck-out effect, which is where the antenna affects the oscillation of the circuit. Here's another 1.8 microhenry choke. This lifts the cathode up above ground and allows the internal feedback capacitors that you can't see, internal capacitance, to produce the Colpitts oscillator. We've got kind of a novel gridley going up to the plate, and this is another trick that Heath Kit used that promotes the squegging and also provides the unstable grid situation, which gives us the high sensitivity at certain points in the cycle. Notice I've added a bias network down here. This is there just because I saw it in a bunch of schematics. It basically can go from 0 to about 8 volts, and I didn't see much difference in using this circuit. I just added it just to play around with it. It didn't hurt the circuit, and I left it in there. We go into the regeneration control, which basically it gives you a range of about 0 to 40 volts, and you end up with about 20 volts on the plate when it begins to super regenerate. By 30 or 40 volts, it certainly is into full super regeneration. We pick off the audio across this 68K resistor. Feel free to increase this value. The higher the value, the more audio you get. I've lightly coupled off with the 001 because we have such a high value audio potentiometer for volume that you don't need anything more than 001. And if you were to put a 0.1 here, I think you'd begin to load this and you may disturb the circuit. Some people may recognize this as a grid stopper arrangement. Well, not really, because we're adding a capacitor to ground, so it really becomes just a low-pass filter to get rid of any remnants of high-frequency squegging and quenching from getting into the audio chain. A very conventional audio chain, by the way. R11 and C15 set up a load line on the first stage. This runs at about 25 or 30 volts, maybe higher, 40 volts. You've got a nice 100-volt rail, so if you can be someplace above 20 volts and below 70 volts, this stage will work fine. Then we go into the power amplifier stage that drives the speaker. Again, we have a biasing network. Feel free to use more than 100 volts here. I just got the 100 volts because that's what my supply did. It certainly would work up to a couple hundred volts, no problem. And you might be able to get it to run as low as 80 volts. So that's the whole circuit and my first experience trying to do a screen capture. Hopefully you guys are able to follow with this colorful pointer.
So this circuit represents a little bit more work than what I usually do on the channel. It is a higher performance receiver. I've tried to work out all of the bugs and kinks and give you a reproducible schematic. You'll notice that the schematic is 4 stages. Even though there's 2 tubes, it's 4 stages, so that's a lot more parts than we usually have in these circuits. But if you take your time, I think this would be a very successful circuit.
So I actually felt sorry for the poor little SDR dongle that I put against this thing. And I'll tell you, my scanner didn't do much better either. This thing has got a sensitivity that's got to be a microvolt or better, and it's really showing some of the magic of the super regenerative receiver. Here's a voltage chart that will help you. It's always nice to have voltages on the schematics because it tells you if you've done something silly like forgot a bias resistor or something, so take a look at that. In the last video in the series, I'm going to do the conversion over to the 12AT7 in the RF and the 12AU7 in the audio. Let's see what we can get. Maybe those 2 tubes are a better choice than the 6BZ7 and the 6AW8. Stay tuned for part 5.